Thanks for having me here. So today I'm going to talk about applying intuitions from AlphaGo to task and motion planning. So the problems that I'm interested in is to enable robots to operate in homes, construction sites, or warehouses in order to autonomously tidy up a place, help workers with the construction, physically demanding tasks at the construction sites, or automate warehouses, right? And all these tasks have some commonalities in them, right? So one commonality is that these problems all involve long planning horizons. So these problems involve orders of not only seconds, but also orders of minutes, hours, and days. If you think about jobs like construction sites, right? And they also involve hybrid decision space, where you've got discrete taskable decisions, such as which object the robot is going to manipulate and in what order. And also they have this continuous motion level decisions that's actually going to realize the taskable decision, right? So these problems could actually be formalized into what's called a task and motion planning problem, where the objective is to achieve some high-level goal, like tidying up a living room, by planning a sequence of low-level motion primitives. So motion primitives could be things like pushing, picking place, throwing, and etc. Okay? So this is solving this problem is the ultimate goal of my current research. So what are some of the approaches for task and motion planning? So one approach would be learning a policy. So you could use reinforcement learning or learning from demonstrations, and then learn a policy that tells you which action that you can execute in the given state. Another approach is to, this is more a traditional robotics approach, where you actually build a planner, you actually make an algorithm that searches different possibilities, right? And then use the planner to solve these long horizon task and motion planning problems. And to learn a policy, I think a most representative algorithm would be deep reinforcement learning algorithms. These algorithms have been applied to domains like Atari games, where they showed superhuman performance. And this is an example of Google Arm Farm, where the objective is to be able to have the robot pick up any object in this bucket by trying different pick and places. So these algorithms have many different successes, but they come with advantages and disadvantages, right? So one advantage is that they're quite fast, in the sense that if you are trying to compute the next action, it just comes down to making a prediction from a neural network, right? So it's really quick to compute the next action to execute. But these algorithms tend to be fragile. So what that means is that if the policy trained with deep reinforcement learning algorithms sees a state that is quite different from the ones that it has seen in training, then it's likely to make mistakes, and it might end up in a state that's even more different than the state that it was in from the training data, and this error could accumulate. And of course, these deep reinforcement learning algorithms are known to be extremely data hungry. They require millions of samples in order to do reasonably well. Okay, so given this advantages and disadvantages, you might be tempted to use a planner, build a planner and actually use a planner to solve task and motion planning problems. And it used to be the case that planning, building a planner was the dominant paradigm in robotics, but now the learning is dominating the field. So I felt like I should show some examples of what planners could do, just to demonstrate that it's still effective. So example here is the work that I did with Anthony Simonov, and what the robot is trying to do is to manipulate the target object to a pose. To a target pose, right? So it plans, a pull motion and then pick in place in order to get it to upright position, right? this work down here is a work by Rachel Holiday. The robot here is a manipulator and an end effector, and there's actually another robot, end effector. And what this robot is trying to do is to use another end effector in order to open the lid of a bottle, right? And it's planning a sequence of motions to do that. And the task here is work by Huang. This is robot that constructs what's called a truss of a building. So truss is basically, you can sort of see it as a skeleton of a building, and it's planning a sequence of robot motions to actually build this complicated shape, right? So these planners, if you give it the right models and the right planning algorithm, can actually do very interesting and diverse set of tasks. But of course, these algorithms also come with advantages and disadvantages. So one advantage is that they tend to be they come with this theoretical guarantee of completeness, right? So if you look at different motion planning algorithms, they at least guarantee probabilistic completeness, most of them, right? And what that means is that given a state, it'll find you a solution eventually if you give it enough planning time, if there is a solution, right? So what that means is that it's very robust to changes in the initial state. But these planners tend to be extremely inefficient in the sense that it does not have a capability to utilize its past planning experience. It always searches from the scratch, even when the problem is similar to the ones that it has seen before. And they're actually computationally inefficient. So it takes a very long time to compute the next action to execute, right? So, we have these two classes of algorithms, right, for solving task and motion planning problem, right? So the question that I asked myself was, can we have the best of both worlds, right? And this led to, what I call meta planning or learning to guide planning. So in meta planning, what you do is that you utilize a planner, but then you use learning to augment it so that you can guide the search based on past planning experience. So you can still guarantee completeness because you're still using a planner that is, say, probabilistically complete or guarantees optimality. But you can also guarantee speed because now you're using learning to guide the search, right? And of course, I wasn't the first one who came up with this idea of meta planning. If you look at a paper by Marvin Minsky back in 1950s, he actually has a paper called Steps Towards Artificial Intelligence, and he talks about this idea, right? He talks about how we can use learning to speed up search. And I think an example that's worth 1,000 words for a meta planning would be this system called AlphaGo, right? So if you look at AlphaGo, it's got a planning algorithm called Monte Carlo tree search that human has designed. And then you augment it with reinforcement learning that learns a value function and policy that guides the search for Monte Carlo tree search. So now, given the success of AlphaGo, one natural question that we might ask ourselves is that, can we directly apply methods in AlphaGo to task and motion planning problems? And unfortunately, the answer is no. And there are two key differences between AlphaGo and task and motion planning. So the first is the difference in the action space. So if you look at the game of Go, you've got board positions, and your action is basically placing a stone on one of these positions. So in the game of Go, despite the large action space, it's got a discrete action space. Now, if you think about task and motion planning problem, for example, here the objective is to move all these blue boxes from this region in here. You've got discrete choices like which object you're going to manipulate, and you've got continuous choices relating to the motion of the robot, such as which base pose you're going to use to pick up an object. So in task and motion planning, you have this hybrid action space. Now, another difference is a difference in state representation. So if you think about the game of Go, you can use the board image as an input to your planner, the value function and policy. But if you think about task and motion planning problem, you have to think about the objects and their relationships in order to solve this complicated long horizon problem. Okay? And you also have, your state representation also has to encode the information about existence of a feasible motion plan. So for example, if the robot is trying to pick up this object, right, you want to know if that action is feasible, right? So your state representation preferably would encode such information. So for these two reasons, you can't just directly apply methods from AlphaGo to task and motion planning problems. And you have to apply some adaptation in order to apply the high-level intuition of using learning to guide search for task and motion planning. So one way to guide search would be to learn a value function, right? So let's say the robot is in this environment and it's got 8 different discrete taskable choices, like picking up object 1 versus object 2, and so on up to picking up object 8. One question that we might ask ourselves is that how do you evaluate the state and discrete action pairs in this situation, right? And for this, we can learn a value function that would answer the question of, is this state and action pair better than this state and action pair, right? And if that's true, then we're gonna explore the subtree, right, below this pick up object 1. So this is one approach that we've explored in the past, and this is what I'm gonna explain next. Okay? There is learning a policy that would guide a search for the continuous motion level decisions, but with the time limit that I have, this is all I get to talk about today. So for this, what we're going to do is that we're going to learn what we call an abstract action value function, right? So this abstract action value function does exactly that. It tells you whether this action is better than this action in this particular initial state. And it's abstract in the sense that this action here is not actually a concrete action, right? It's just an abstract action that tells you, which object are you trying to pick next, right? Okay, so what are the challenges involved in learning a value function for these kinds of abstract action value function, right? So we've got 2 issues. One is, how should we design the objective function for learning an abstract value function for deciding these task level decisions from planning experience, right? And the second is this question of how should we design the input to the network that would represent our task and motion planning problem. So we're going to talk about the first challenge first. So to come up with an objective function to learn our value function, let's just first look at our data, right? So our data consists of a set of planning solutions. So we have experience of solving problem 1 to n, and we've got discrete decision nodes where we decide on the discrete decisions, and continuous decision nodes where we make decisions on the continuous motion level, right? And one trajectory leads to the goal, right? And there are other trajectories that we've explored, but didn't really get to the goal, right? So these are, and we have n number of such search trees that we've have accumulated so far in our planning solutions, right? So given this planning solution, one naive objective function would be to use mean squared error with the cost to go from the start state, from the current state to the goal as a target. So for example, let's say we're here, and let's say we took 10 different actions to get to here. That would create a target for this particular action, right? The value of this action would be minus 10, let's say, right? And we can use mean squared error to learn the value function. Now, the trouble is that we only have the target values for the trajectories that led to the goal. So we would have target values for these sets of actions, but not for these sets of actions that didn't lead to the goal, right? Even though we've explored them, right? So this if you go down this path of using mean square error loss to learn your value function, then you're going to be requiring an extremely large amount of data. Right? So to deal with this problem, we came up with a design principle called pessimism against unseen actions. Okay, so as its name implies, we're going to be pessimistic about the actions that were not in the data set of trajectory in the data set of getting to the goal. Okay, so instead of learning a value function, we're going to learn what we call action rank function that ranks different actions in the given state. And the way we're going to learn this function is by penalizing actions that were not in a path to the goal. Okay. So let's see how that looks like. So here, E is a set of trajectories that led to the goal, right? And F theta is our rank function. So this outputs some value, and this higher this value, the higher the rank of that action in the given state. Okay. So if you look at this objective function, the first term is trying to maximize the rank value of the state and action pair that led to the goal. And the second term is trying to minimize the max rank value of the actions that were not in the data set. So it's trying to minimize the rank values of all the other actions that did not lead to the goal. Okay. So by doing this, we are being pessimistic against actions that were not in the data set, right? So we don't know if they will eventually lead to a solution, but we're first going to be pessimistic about them because given the data that we have in our E, this is the best we can do. Okay. Okay, so for this challenge, we were able to come up with this principle and use ranking function to learn our rank value function that guides our search in a data efficient manner. But what about this challenge of designing the input to the network, right? So to solve this problem, we looked at different planning literatures, right? So and we realized that there's this overarching theme in guiding a planner, which was that in most of the planning algorithms, what they do is that they first use relaxed problem representation of the original problem as an input to a planner, and then use the planner to solve that relaxed problem, and then use the output, basically a solution of the relaxed problem as a plan guidance. So you can use that to define a heuristic function. I think one close example would be for collision-free trajectory optimization algorithms. What you can do is that you can define a relaxed problem by ignoring all the obstacles and then initializing the solution with a straight line path to the goal, and use that as the initial seed for your optimization, right? So that's an example of using a relaxed problem representation to guide your search for the original problem. Okay. So this is a decade-old idea, but the problem here is that because we have this long horizon problem that involves a hybrid decision space, even a relaxed problem representation is difficult to solve using a traditional planner. So what we're going to do is that we're going to, instead of using a planner, we're going to use neural network to take the relaxed problem representation as an input. And instead of planning, we're going to use learning to solve the relaxed problem. Okay? And then we're going to use the output as the output of the neural network as the planning guidance. Okay? So how can you do this for abstract actions? So the abstract actions involve things like deciding things like which object to manipulate, what order, and using which manipulation primitive, right? And so to do this, what we decided to do is to represent the problem abstractly, ignoring all the geometric details such as poses and shapes of the objects. Okay. And to do this, what we did is that we designed what's called geometric predicates. So these are a set of Boolean functions that tells you certain facts about the environment, such as whether the object is reachable, whether one object includes another object, and so on. Okay. So based on this geometric predicate, given a task and motion planning scene like this, we can have an abstract state that consists of evaluation of these predicates. So for example, we can have a reachable predicate for this particular object, evaluated to false because there are obstacles occluding the path to the target object. And we can also have occludes predicate evaluated to true for this to indicate that these two objects are occluding this object here, right? And you can evaluate these predicates for all the other objects in the scene, and to process this kind of relational information, we represent them in a graph and use graph neural networks to use them and process them, right? So here we have this relational abstract state representation, right? And each node of our graph is about the object, right? And each edge of our graph is about the relationship between two different entities in the scene, right? Okay, so that was about the representation and the neural network architecture, but you might be wondering, how we can compute these predicates, right? So one thing that we can realize is that these predicates are about reachability, right, and occlusion in a scene. So we can use robot motion planning algorithms to actually, compute these predicates. So the overall computation of our framework is that you're given, planning problems like these, right, task and motion planning problems like these. You're going to perform low-level geometric reasoning using motion planning algorithms, right? And that's going to give you the abstract state, that tells you the information regarding the occlusion and reachability of different objects, right? And then using that, based on that abstract state, we can perform high-level reasoning, right? Using that rank function that we trained using that the loss function that I showed you earlier, right? So now we can apply this guidance provided by this f theta to our planning algorithm, right? So this we've applied this algorithm to this domain where the robot is supposed to move all these blue boxes from this region to this region. So this is sort of like a mover robot that needs to unload boxes from a moving truck, right? And it's got different movable obstacles that are in the way, right? And here is a plan that it found where it uses the planner that is guided by the rank function on deciding which object to manipulate at each state. Okay. And because we're using this abstract state representation, we can actually collect data in environment that looks like this and apply to an environment that looks quite different in terms of geometry, so shapes and poses of the objects. So we only collect our data in this environment, right? But apply to a domain where now your goal is to retrieve the target object in yellow from the shelf, and you have to put it inside the box, right? Without retraining. So here is a plan that the robot has found using a planner plus the guidance from the ranking function, right? That did not use retraining in this new environment, right? And you can see that it retrieves the target object and puts it to the goal. So so here are some results, right? So on the y-axis are the planning time, right? So this we have 2,000 seconds as our planning time limit for the domains that I showed you earlier. And for pure learning, so for pure reinforcement learning, because of this long horizon nature of this problem, it doesn't do so well. The median is that it times out. But because this is fast, there are some outliers that can solve problems, some problems quite fast, right? And here are the results for pure planning methods, which is better than learning because it's now performing these long horizon reasoning, right? So here is the result for the state-of-the-art planner. This is our algorithm, our own planning algorithm, plus the heuristic function that we designed. And here is our planner guided by the ranking function. And you can see that, compared to the state-of-the-art planner, right, there's about 3 times of speed up in solving these problems. Okay. So some of the takeaways is that, for these kinds of long horizon planning problems, use meta planning to guide a planner instead of using pure learning or pure planning alone. And to design a data efficient objective function, you should think about using the principle of pessimism against unseen actions. And to design an input to the value function and policy for these kinds of complicated task and motion planning problems, you can use the principle of relaxed problem representation. And there are more information about this in our recent paper, so you could take a look at that. And with that, I'll wrap up my presentation and accept any questions that you might have.